Hardy-Weinberg equilibrium is a model, and it's based on the Hardy-Weinberg law, which describes what happens to alleles and genotypes in an ideal population that is infinitely large and randomly mating and not undergoing evolution. The Hardy-Weinberg law makes two assumptions about a population. The first assumption is that the frequencies of alleles in the gene pool don't change. Now, usually when we are using Hardy-Weinberg, we're just looking at one trait, one allele. So Hardy-Weinberg law is assuming that the frequencies of the dominant and recessive alleles for this particular trait in the gene pool are not changing over time. It also states, it makes the assumption that the Hardy-Weinberg calculation, which is p squared plus 2pq plus q squared, can be used to show the frequencies of genotypes after one generation of random mating in this population. The genotypes that are associated with this equation are the following. P squared is equal to big A. So P is equal to the frequency of A. Q squared is equal to little a, so Q is equal to the frequency of little a. We always express these frequencies as a number, not as a percentage. So if we say that 25% of a population has the recessive phenotype, meaning that they've got to be little a for their genotype, that 25% needs to be expressed when you're doing the calculations as a number, 0.25. When we're looking at just two versions of a gene, big A and little a, the dominant and the recessive, for any particular gene, they're going to be the only copies of that gene that are present in the population. So they, if we add together big A and little a, they're going to equal 100% of the alleles for that particular gene in the population. So P and Q will equal 1. P and Q equal 1. If P and Q equal 1, then that means that if we can learn the value for one of these, we can actually use it to plug into the Hardy-Weinberg equation and calculate the frequencies of the different genotypes that are present. Okay, so let's say that we've got a population that has got a frequency of the recessive phenotype for some gene of 4%. Okay, so a frequency of 4%. Since the problem is referring to the recessive phenotype, we know that that's going to be little a. A 4% frequency of that genotype, which means a 4% frequency of the recessive phenotype. If we turn this into a number, we get 0.04. So the frequency of this genotype is 0.04. From that, because we know that AA is equal to value in the Hardy-Weinberg equation of Q squared, we can take the frequency of little a and take the square root of it and come up with a value for Q. So in this case, Q equals 0.2. Now, we learned already that P plus Q equals 1. So now we can get Q easily. 1 minus 0.2 is going to equal P, so P is going to equal 0.8. Now, we've got our p-value, we've got our q-value. We can work our equation and figure out the frequencies of all of the genotypes in the population, and from those we can even figure out the frequencies of the phenotypes. Okay, so the frequency of the dominant homozygous phenotype is going to be 0.8 squared. The frequency of the heterozygote is going to be just the frequencies of the homozygotes, the frequencies of P and Q times 2, and the frequency of the homozygous recessive will be Q squared, and these will all add up to 1. So let's say we want to know, let's say in our population, we want to know the percent of individuals who are heterozygous. The percent of individuals who are heterozygous. Well, all we have to do is figure out the frequency of the individuals that are heterozygous. And that frequency here is going to be equivalent to 2pq. 2pq is 2 times 0.8 times 0.2. That's equal to 0.32. Now, what we have to keep in mind is we need to give a percent for that. That's going to be 32%. So if your population is 100 individuals, then you'd have 32 individuals that are heterozygotes. Another word for heterozygote is carrier. Because they look dominant, but have a recessive allele. What if for the same population, we wanted to know how many individuals would have the dominant phenotype? Well, in this case, we know that the definition of a dominant gene is any allele that is expressed whenever it's present. So this is going to be the sum of these two frequencies. Okay, so here we've got P is 0.8, so we're going to have 0.8 squared plus 2 times 0.8 times 0.2, and this is going to give us, this value will give us our number, our percent or proportion of individuals that have the dominant phenotype. So all we need to do is to figure out what our values are. We've got 0.64, we've got, what was our 0.32, we're going to add those up, give us 0.96, 96% are going to have the dominant phenotype. If we've got 100 individuals, 96 out of our 100 are going to have the dominant phenotype. What you've probably noticed by now is that the important thing when you're working Hardy-Weinberg problems is to understand what is the data. What's the data that you're being given? That's going to allow you to answer the question properly. What's the data? If the data is phenotype, you're going to be looking for P squared or 2PQ or Q squared. If the data is alleles, So the percent or the proportion of alleles, you're going to be looking for P or Q. This is going to be very important for you. If you're told that the frequency of the recessive allele is a particular number, let's say 0.2, if the frequency of the recessive allele is 0.2, then you know right now that you've got a Q of 0.2. You can immediately calculate your P and go on with your equation. So when you're working a Hardy-Weinberg problem, you want to make sure that you know what's your data, and you need to know whether you're being asked to work with percents or proportions, which you're going to express obviously as a percent value, or frequency. A frequency is going to be a decimal value less than 1 that relates to your percent. A percent of 25% is equal to 0.25 frequency. Keeping track of the type of data and whether you're working with percents or frequency is going to make a big difference in being able to do Hardy-Weinberg equations.